All right, so in the last video, we addressed this statement, which is to say that if you have a function and then you produce a function off of that function, which is a function tracking the area under the curve, then the derivative of that function based in terms of integral is going to be the original function that you started with, which kind of makes sense, but well, you could have some interesting examples related to it. So here's an example. Let's say this. If g of x is equal to the integral from 3 to x of sine t over t squared plus 2 dt, find g prime of x. This is actually a direct example related to our situation. Because you see, we're trying to take the derivative of this integral function, which is between a constant and x of some function of t. Well, the long story short here is that the derivative gives you back what's inside, and the derivative would be sine of x over x squared plus 2. One subtlety here is to note that while the original function was in terms of t, whenever we were computing the area under the curve, that came out in terms of x. So the function g is indeed in terms of x, and whenever we did that computation for the area under the curve, that's going to be dependent upon whatever x is, and that's why the function pops out with respect to x. Our original function is with respect to x, then the derivative function will be with respect to x. What about this example? Here's one that's a little less cookie cutter, but sort of similar in construct. So what if g of x was equal to the integral from x to 10 of e to the minus x squared plus 5, or excuse me, e to the minus t squared plus 5 dt. Find g prime of x. So here is a function expressed in terms of an integral. And we want to try to find the derivative of this function defined in terms of antiderivative. Now, when you have a function with a constant, between a constant and x of your function, and the function is defined in terms of the antiderivative, you take the derivative, you end up getting what's back inside. Note, this is not exactly that. The bounds here have been flipped. So if the bounds were constant to x, you would get the same function back. But since the function is not that, we'll first correct it so that it is. And then we can apply the fact. So once we get the bounds between c and x, now we can apply the fact that we deduced, which is to say the derivative of the integral gives you what's inside. But of course in terms of x, because the original function was in terms of x, that was our thing that was varied. So the long story short is if you happen to get the bounds cooked up in a way where they're reverse of what you would need in order to apply the fact, then you simply flip the bounds. You know flipping the bounds flips the sign on the integral, and that problem solved. I'll go through one more example here that's going to be a little bit harder, but it's going to actually show off quite a bit of calculus skill, and something that would show off a lot of calculus skill. And let me go through that here in the next video.